My name's Claude Meffan. I'm a PhD student from the University of Canterbury in Christchurch in New Zealand. And I'm going to be talking to you about the thermal conductivity of polymethyl methacrylate silicon dioxide superlattices. So to give you a brief overview of the talk I'm going to do, I'm first going to start with a little bit of an introduction and a motivation and talk to you a little bit about what phononic crystals are and what their potential uses in sensing might be. And I'm going to talk to you a little bit about the methodology that I use to measure the thermal properties of these crystals. And then I'm going to go into a little bit of characterization and a little bit of an outlook on the future of what I think these phononic crystals might be able to produce. Okay, so phononic band, this superlattice that I'm investigating is part of a wider family of materials called phononic bandgap materials. So a phononic bandgap material is a material which has a vibrational bandgap. There is a range of thermal energy carriers in a certain frequency band which are forbidden from propagating through the layers of this material. This hasn't been incredibly well studied in the past, namely because the scale that you have to fabricate on to do this kind of work is usually incredibly small and fine. However, it has picked up in recent years with nanoelectronics starting to get to the point where we are fabricating on this length scale. Some of the proposed uses for this so far have included things like thermal mirrors, where multiple in-phase thermal reflections come off the layers and create a total thermal reflection through the material. People have also made things like thermal diodes here, which have an order of magnitude more thermal conduction in one direction. The specific work that we're building on in this area, though, is called a photonic crystal, which is a little bit of a buzzword, I know, but this is a material which has both a photonic and phononic bandgap, which share a common wavelength and enables light-matter interaction. So some of the proposed uses for this include light-matter interaction, so wavelength modulation by hypersound. Also, it has been proposed for use as a biochemical sensor, where you can see both a change in the speed of sound and also the refractive index together. So why am I going to measure the thermal conductivity of this material? Well, in both polymethyl methacrylate and silicon dioxide, they're both dielectric materials. So the primary thermal energy carrier in these materials is phonons. So by measuring the thermal conductivity of the material, I can then extrapolate or correlate what the phononic behavior of the crystal is. So first I'll talk to you about the superlayer structure that I made and how it was fabricated. So like we just saw, this kind of superlayer structure is a variation in material, so it's a stack of different thin films on top of each other. In a photonic crystal, you're varying the refractive index by layer, and in a phononic crystal, you vary the acoustic properties, namely the speed of sound and the density of the material. So both PMMA and silicon dioxide have a large difference in their acoustic properties, and so you get reflection off the interfaces. Although I know I just said it's usually a very, very fine process to be able to fabricate these crystals. However, we have based our work and continue to work on a spin coating methodology, which has been studied before. And this has shown that it's able to produce a reliable phononic bandgap and also at room temperature, which are two of the key areas which we wanted to work in. So what we did is we had a liquid phase of PMMA and we spun coated that and baked it. And then we had a colloidal nanoparticle dispersion, which we spun onto the top of that, and we just rinse repeated that until we had the appropriate amount of layers. So now I'll talk about the technique that I used to measure this material, which was AC resistance thermometry. So the basis of this technique is we fabricate a titanium gold resistance thermometer on the surface of our superlattice crystal. But then applying an AC current through it, we're able to create thermal waves which penetrate through the material. And then by monitoring the third harmonic of our electrical driving frequency, we can monitor the temperature at the surface of our superlattice. By then comparing that to a control sample, you can isolate what the effect on the thermal conduction of the superlattice structure alone is, and therefore work backwards to the thermal conductivity and the thermal diffusivity, if you wish. So because our superladder structure was comprised of PMMA, which is solvent sensitive, we weren't actually able to use any of the conventional lift-off based patterning techniques. So instead we opted for a shadow masking procedure, which we fabricated with a CNC micromill. So over here you can see this is a 50 micrometer diameter end mill cutter approaching the surface of some brass shim. We then use this to cut a negative of the resistance thermometer shape that we wished into the surface of the brass shim. We then pressure mounted this to the top of our samples and evaporated titanium and gold through that. So here are some SEM micrographs of what our superlattice ended up like. We studied 3 different periodicities, which ranged between 85 nanometers at the low end and 105 nanometers at the high end. We had a little bit of an issue in that because the silicon dioxide nanoparticles are porous, the PMMA solution would tend to flow into it. And so across all of our different architectures, we did see a reduced PMMA thickness, which is possibly has broken the periodicity a little bit. So this is an example of the kind of data out that you get from an AC resistance thermometry experiment. So over here, you can see this top green line represents a frequency sweep, a full thermal transfer function sweep of the superlattice sample. And then below, you can see the control, the substrate only sweep there, which all this means is that the distance between these 2 lines implies the thermal conduction of the superlattice alone. So we measured a value between 0.023 watts per meter Kelvin at the low end and 0.033 at the high end. This is all done at room temperature and atmospheric pressure. These numbers, for those not familiar with thermal conductivity ranges, is a reduction of about 1 or 2 orders of magnitude, depending on what you compare it to the bulk, which is really quite large, especially for a room temperature measurement. The original authors or the original creators of this particular phononic crystal reported an increase in the bandgap of the phononic material with a decreasing period, which is what you would expect. However, when we tried to correlate this with thermal conductivity, we got a moderate R-squared value at best, which sort of essentially implies that there is another mechanism at work here at room temperature when measuring the sort of integral of all the thermal energy carriers via the thermal conductivity. So with this in mind, we sort of started to seek out what might be the overall mechanism operating behind this thermal conductivity reduction. And we started evaluating it with respect to existing models. The one we eventually settled on and evaluated was a packed nanoparticle bed, so essentially evaluating the thermal conduction within one single nanoparticle layer. So the basis of this is that for a phonon of certain frequency, trying to traverse from the body of one nanoparticle to the other, it has to funnel itself through this very small nanoconstriction here. And what you end up finding is that the phonons trying to traverse between 2 nanoparticles are filtered relative to the area of the nanoconstriction, relative to the body of the nanoparticle size in itself. And this nanoparticle radius here is not actually simply a function of geometry. It is also a function of the surface energy of the nanoparticles and also the external force put upon it. In our bed, because we're not putting any external force upon it, it essentially becomes just a function of the nanoparticle surface energy. So this is a little bit of analysis of our nanoparticles and essentially trying to adapt what we found in this existing model to our system. So when observing the nanoparticles from above, we found that our nanoparticles had an average diameter of about 22 nanometers. and they actually had a really high surface energy for what we expected. They were able to hold together into a layer, and contact angle measurements revealed that they had an extremely hydrophilic type behavior. We also noted that there is a pretty high density in pinhole defects in one single sheet of nanoparticles. So that could be one reason why our periodicity versus thermal conductivity did not have a particularly strong correlation. We don't have a way of assessing what the defects are through multiple layers. So that could be one reason why we didn't see as strong a correlation as other people have reported. So essentially, what are my conclusions from this? It seems that our nanoparticle polymer superlattices have a really strong reduction in thermal conductivity with respect to bulk. It's been between 2 and 1 orders of magnitude with respect to the polymer and the bulk silicon dioxide. And it appears that the nanoparticles in particular, based on other work and modelling, seem to be a key player in all of this. So if we're attempting to maximise the phononic bandgap in future, I think it's really worth investigating and pushing forward with the nanoparticle morphology in particular. I think that perhaps using nanoparticles for the low density layer as well as the high density layer could yield good results, as well as creating a sort of pseudo phononic crystal within a single layer by varying nanoparticle composition inside of a single layer. Okay, that's pretty much all I have. I'd just quickly like to thank my funders, and if any of you would like to talk to me beyond questions here, you can contact me on my email, or you can talk to me on Twitter if that is your preferred method of communication. Thank you.